Let's get the annotation going. All right. Let's see where we are. We have the cut vertices pages to read over. Any questions on any of this? It's basically just part of the graph that can cause the graph to become disconnected if we were to remove that part of the graph. Everyone's quiet tonight. Okay, moving along then to the next section, hashing. Still need to break this into separate files. 7 pages is a bit long for one, but what do we have at the moment, if we have anything? Okay, let's go ahead and take a look at salty hash. Code is in the files section under hashing. It's just a C# application just to show how we can generate salt, get that combined in together with whatever key we're hashing. Take a look at the code later. The point of this one isn't the code, but rather the pattern. All right, so in sample application, we go some website, create an account. All right, the first level of security that we can have is to at least just hash your password. Problem is just hashing your password, at least with MD5, it's not the greatest security methods, because if you just go ahead and just search the hash value, you can very easily see that it's already been dictionary attacked. So all words, all common combinations of words, and you can see that it pops up very quickly to find out what the hash value is. So the security of a hashed password that's just plain hashed with MD5 is not much security at all at that point. So that's where we want to go ahead and have a salt come along with it. It's now in the same user with the same password, comes along in there, and then they hash their password. Trying to search for this, it's not likely to find any results, right? Because attempting to build the reverse lookup for all possible combinations of characters and all that fun stuff just becomes too much data to try to store in a preemptive attack. Now, much different story if the data gets compromised, right? If someone compromises our data set and they get the salt, and they can take this salt and take that against all common passwords, right? Names, words, common substitutions, things along those lines. And then we can have some data compromise, but that's still going to take some time. And that's basically all security is it's attempting to slow down someone who is attempting to breach the system. And if you make the amount of time that it takes to even breach the system, even if the data is compromised, so long, then most people or most actors are going to go ahead and move along to the next system. So we're always trying to go for easy targets. That's the wrong button. You can change my password here. I'm going to go and capitalize one of the letters in the name. Then register that user, and let's compare both of these hashes. May using the same word, however, there's a single bit difference between uppercase and lowercase characters in the ASCII or Unicode table. You can see the corresponding hashed password is significantly different. So that's a good sign for a good hash algorithm. So as far as just using MD5 for hashing, in a non-secure sense, it's a perfectly fine hash. It's just when it comes along to using it for security purposes that we lose any value in it. I'll show you the code really quickly. There's not a whole lot of excitement going on here. We'll get this little function. If there is a salt, it just concatenates the password and the salt together. Otherwise, it's just an empty salt. And we use the built-in library to generate a hash from our MD5. And we store it into the database. So when the user comes along.
Sorry, Professor, did you say MD5?
I said MD5. So MD5 is our message digest 5. It's one of the standard hash algorithms. MD and SHA, secure hash algorithm, are the most common. All right, so when the user comes along and they want to log in, right, they type their username, they type their password, they try to log in, and we should go ahead and hash the password along with the salt that we looked up, and then they're good to go. If they go, user types the wrong password, then the login is going to fail because it's statistically unlikely for a different key to end up to the same hash value. All right, so we take some data, throw it through our hash function. The hash function produces the hash value, which we see here in a hashed password column. Salt is just a random value. So if we look at the code where I generate the salt, where do we generate the salt? That's right, it's my other button. Where's my other button? There's create salt. So here is just the random number generator. So the RNG random number generator. This is using a secure provider to try to create more secure random numbers. But it just populates this with a bunch of random bytes. And we convert that to a base 64 string so that we can put it into our text box and doesn't do any weird stuff. So the idea will be for each new user, each user gets their own salt. They register. Right now it protects. So even if they're using the same password, because each person would have their own salt, even people, same password, show up here in completely different hash passwords because they're different salts. So different salt appended on or mixed in, depending on how sophisticated you want to be, into the data. Right? That's the other way. It's often called security through obscurity, where you're protecting things by just trying to hide how basically the keys are on the front porch somewhere. The door's locked, but the keys are out there. So you just hide the keys. And if no one finds the keys, then the door can stay locked. But if someone finds the keys, then it reduces the security of things a little bit. Because there's all kinds of different ways we could fold the salt in with the password. Right? We can see how long the password is and break the salt into pieces and then interleave first few characters of the salt after the first character of the password, then grab the next couple characters and then keep mixing these two together, kind of like some of our hash functions do where they chop it up, mix together. So we apply a similar strategy with the password and the salt or every user, as long as the way that we register the user follows the same pattern as they are using to try to log in, then we're good to go. Try to fold things differently, right? We can't be random between attempts. It needs to be deterministic. A given key yields a given value. Just here, our key is a composite of the user's actual password and a salt that we assigned to them when they registered. So whenever they go ahead and log in, we go to the database, go find Bob2. All right, so Bob2 is trying to log in. Find Bob Salt, take the password that they provided to us, blend that with the salt again, just like the way we did when they registered, and then we can compare that resulting hash value, just right here in this box, to what we stored in the database. And if they're a match, then we know this is the correct password. And if even just a single bit is wrong, trying to log in isn't going to work because the corresponding value is not going to match up. Yeah, the salt goes through the hash function, right? Because we take the password and the salt, concatenate those together, and then we go ahead and run that through the compute hash function. Where we passed salt and password to our MD5 function here, and then calls compute hash and just pumps the bytes of data that is that string into this fixed output of bytes. Let's see, I don't think there's anything else I should put on the code. All right, my database is just an array of data that we're storing in memory. And so every time we run the program, it's just going to be reset. All right, we generate salt for the purposes of security. All right, that's the idea of a salty hash, because not doing it, right? Let's say our password's happy. Get about salt. All right, the password here isn't well protected at all because MD5 is, oh, really? Happy capitalized got past it. Let's see. You get the right value. Let's see, that's Bob22. Yep. Fascinating. Happy actually made it through. Let me uncapitalize happy and register another Bob. Let's see how well this version of happy. There we go. Found it. It's funny, just capitalizing H was enough to keep us out of, let's see, hash killer. Hopefully this isn't too bad. No, want to be downloading files from the internet. That's a bad idea. Just a .text file, but, you know, there's always a potential problem there. Okay. Let's see. Yeah. There we go, happy. And so this hash value, right? So it's not mathematically possible to go from the hash value to go back to see what generated it, but you can go ahead and hash all the words of the dictionary and then store their hash values, and then you just can do a reverse lookup to go back to it. So just capitalizing the letter was enough to escape these reverse dictionary attacks. Right, it's just like your name in the phone book, digital or physical, corresponds to an entry in the addresses, right? So Bob Smith lives at 1550 Irvine Center Drive or Irvine 92620 type thing. Your reverse lookup, right, goes the other way around. Or say it's like a telephone book, right? Bob Smith's phone numbers, you know, 714-555-1234 type thing. The reverse lookup is to have phone numbers first, and then you can see who belongs or is associated with that phone number. Same idea here. You run through the MD5. The whole suite of dictionary words, because it's a standard algorithm, so it's commonly used. It has been secure for a good long while, 2004. It's still used for other things where security isn't the issue. If you want to just do data integrity checking just to make sure the 2 megabyte file or 2 gigabyte file I just downloaded is correct, all the bits are correct, we can feed that 2 gigabyte file into a hash function, and it spits out that particular hash value that's only likely to be correct if every single bit in those 2 gigabytes of bits are in proper order and state. Just toggling a single bit in the data cause the hash function to produce a wildly different value, right? Like we saw where's the program over here. All right, just a little slight difference between the two values, these two Bobs, one had a capital H, one had a lowercase h, and it produces an entirely different value, which means that there's not a match in the originating data. Adding salt enables us to securely store data, or substantially more securely store the data in a way that if the data set is compromised, that people's accounts aren't likely to be in a problematic state, or at least it buys us time so we can go in and reset everyone's password, tell everyone you need to log in again, log in with your old password. That's going to take you to a screen that says you need to change your password type thing, and do further authentication so we know that you're you and not whoever was that stole the data set and is attempting to crack the system. Right? And the other way, this helps because it's very common for usernames, right? bob2@gmail.com generates the account for my fake website here. That gives you 75% off coupons for everything. So go ahead and register a free account. right? So we can go ahead and steal your password and all that fun, good stuff, and then use it on all bunch of other sites where you might have used the same username and password. Right, so it's always highly recommended that you use a different password for every place that you need to create a password for. No, don't need to know the details. It's down in here. Right, here's the algorithm part. Right, we're just breaking apart the data into pieces and then folding them back together. So no, you don't need to memorize this little detail here. We will talk about it briefly. What do I think about LastPass? I don't trust third parties storing passwords beyond Google. I do let Google store my passwords in Chrome, but I don't let them store my bank passwords. Right? I log into my cellular provider or Hulu, Netflix, things like that. If my account gets compromised, it's not a big deal. But they get my bank password and all of a sudden just transfer all my money out. Yeah, that's a little bit more of a risk tolerance that I'm going to go ahead and just memorize my password, not write it down, and not let any system have it. But for LastPass or Chrome, for things that are managing my trash service, automatically paying that, I'm not going to worry about. But anything that's financial based for my money, that is out of their zone, because they wouldn't be using hashing. They would just be encrypting it. So because they need to be able to decrypt the data to get back the password back out to go ahead and put it onto the form in the browser. And the internet's got lots of caches out there, and there's always risk. They're decrypting the password, right? So hashing for cryptography is one area of cryptography. It's one-way cryptography. There's also two-way cryptography, right? Just like HTTPS, right? So this session I have here with Wikipedia is over TLS connection, where all of the data that I send to them and all the data that they send back to me is through an encrypted tunnel, right? So a handshake was done, basically more or less a password or a key was exchanged so that I can go ahead and throw the data through an encryption algorithm in such a way that typically with their public key in there, you can use their private key to go ahead and decrypt that data. And that level of cryptography is beyond the scope of our class. And that's where the math starts to get serious when you get to symmetric and asymmetric cryptography. All right, so Chrome or LastPass would not be hashing your password. They would be encrypting your password. And ideally, they're using a per user key. Right, so every user has their own key. So if like one key is compromised, it's only compromising one data set, but they probably have an encryption key that encrypts all those keys type thing. There's always somewhere in the system where there's access. The software itself has access, and then the administrators to the system are going to have some level of access and be able to see things. So the greatest risks are from internal sources. Yeah, so that brute force dictionary attack is how my hashed values, my hashed passwords that I was saving, tossing those into Google, we were getting hits because those have the dictionary attack. And they're pre-done. But if our data was compromised, right? So if these 4 records were compromised, they actually have salt, right? These passwords are gonna be quicker to go ahead and crack because we can pre-run the attack. we've gone ahead and taken all the common words, already gone through there's already websites that have them out there. You just pull the data down. You do the reverse lookup. Now, when it gets to these 4 records, that pre-attack is kind of useless unless you want to do the pre-attack on all of the different, let's see, it's 4, so let's do it. 2, 4, 6, 8, 10, 11. 1 second. Let's see. All right, when I say a dozen, let's get my calculator right here. Calculator. So we've got base 64 to the 12th power. And so 1, 2, 3, 4, 5, 6, 7, 8 groups. What is that? Million, billion, trillion. I don't want too many. There's this many possible. Let's divide this by gigabytes. Oops. Divided by gigabytes, kilobytes. Now we're into megabytes, and now we're into gigabytes. 4 trillion gigabytes. Is that right? Million, billion, yeah. So 4 trillion gigabytes of possible salts multiplied against the dictionary of words I think people might be using as passwords. And it's just with the current computing and memory technologies that we have at the moment, it's just ridiculous. You know, in 10, 20, 30 years, 4 trillion gigabytes might be a tiny amount of data, you know, DNA data type storage and all kinds of things like that. Quantum, and whoever knows what's next down the line. And at that point, that's where we need to get things bigger, right? So we go ahead and double the size of the salt. All right, and then this number gets that much bigger, right? 64, so if I break the calculator. So you have 24 characters. All right, scientific notation here now, raise to the power of 43. This is why you'll see encryption, right? It used to be 128-bit, and it jumped to 256, then jumped to 512, then jumped to 1024, and I think 2048 is starting to become probably what's being used by the Department of Defense and other extremely high level security type installations where we don't want people to have any sort of chance with any specially built hardware of getting in there anytime soon. And just doubling the number of bits substantially grows how big the footprint of these is going to be if we're trying to break them into them. Question is, I guess some salt could be better than other salts because random libraries are better than others. Yeah, depending on, you need a random number generator that it can actually give you a proper distribution across the full range of values that you're asking for. Typically, the built-in basic RNG generators are just a little mathematical progression and not all that great for a normalized distribution. Okay. Let's go ahead and look at the code. All right, still in the hashing folder and files. Online compilers happy tonight. Seems I could use some white space in here, but that's fine. We'll take a look at the output first. All right, so we're inserting some values at some location in the table. And until we end up with a collision, we'll go ahead and do our collision resolution, right? So now what we're doing is still hashing, but another usage of the pattern of hashing data, right? So the first pattern we were just looking at was for just protecting data as we store it. So we take the data, run it through a hash function, and then we go ahead and store the hash value. One of the other things we can do with hashing, it's quite common, is to go ahead and create a hash table, often called a hash map or a dictionary. Purpose of that data store and that data structure is fast lookup, fast data insertion, fast data retrieval of that key or the associated data if there's data associated with that key. So what we're doing here is we're just tossing some data into the table. Of course, tossing the same key in there is guaranteed to cause a collision. Where a collision is two keys wanting to occupy the same position inside our table, and the table is basically just an array. And when we have that problem, we need to go ahead and push that data somewhere else. So look at our linear probing code here in a minute. I did find a home over here, position 11. And we kept tossing in more data. And we didn't have too many collisions, but as the table gets full, our load factor increases and the probability of a collision increases. And it gets to a point where the table is getting pretty full and completely full up to this point, so we can't actually add anything. Right? If the house is full, you can't add any more people into the occupancy there. Okay, so here is our hash table. So class hash table. Here is our array. This is where the values will actually be stored. If this is a key value pair, then we just need to change the data type of the table to support the key value pair, so we can have the key and the value stored in there. Our hash function that we have in here is our basic hash function modulo the table size. So whatever the value is, and we're just playing with integers because integers is the last step to becoming an index into the table. Through our hash function, which is just data modulo size. And if the table doesn't have an occupant at that particular location in the array, we just go ahead and drop the value into the table. Indicate that our insert was successful. Carry on. Otherwise, we need to find an alternate location. All right, so with probe being our basic open addressing, our linear probing being our basic open addressing approach for finding a new position. What we're going to do is just going to go ahead and take the location of our collision. All right, so we take our data, ran it through the hash function again, get our collision point, and then start probing away from there. We'll go ahead and go one away from that location, and then modulo size. All right, because remember, we want to treat the array as a circular array. We'll try to go beyond the end of the array. We'll just roll right back to the beginning. This is what we're doing. We're normalizing the data so that we can make sure that we stay inside the boundaries of the table. Here is our exit condition in case the table's full, because this particular source code is not keeping track of the count. It'll be a much quicker way to get out by just tracking the count, because if there's 17 spots in the table and we have 17 values in the table's full, no new values cannot be accommodated at that point. All right, so keep looking for an empty position in the table. If we find it, we can drop the data in like we did before, return true. Otherwise, we'll just go ahead and increment. Doing it prefix, we can go ahead and get the increment first and then modulo size to keep it in range. just keep looking for the next available spot until we find an empty cell and we can drop our data in. All right, I don't have the lookup code here, but the lookup code is going to be very similar to the insert. Go ahead and calculate where we are. Look to see if the data matches. Right? If this location has our data, we're good to go. If it's empty, then our data does not exist in the table. Go ahead and return back false that the data doesn't exist. And if we find, right, we're doing a lookup for 15 and we found 12 in the table where we are. Okay, we've detected a potential collision that happened when we populated 15 into the table. So we'll do like we did before. We need to dig through the records until we find who we're looking for. So any questions about the code file here? Let's see. Question is, ask us to use a sign in our passwords. Oh, yeah, special symbols, because special symbols are often not used in the dictionary attacks because there's a lot of special symbols. So it's just increasing the complexity. Yeah, so it's very common when you register for a site, they'll have rules that you must adhere to for the password length. That really hits some of them like, it has to be between 6 and 8 characters. It's like, oh my God, your system is so old that it can't store small passwords, or it's not even hashing it because it doesn't even matter how long the password is. If we're hashing it, it's going to be the same length, whether it's short or long. But the primary driver is protecting the password from a dictionary attack, because they're probably at least hashing it, right? If they're going through the effort of bothering to enforce rules upon you, how sophisticated your password needs to be, right? So it's twofold: they're protecting you and they're protecting the system, right? Because even if someone forces their way into your account and they steal your money from your, well, you're rid of your prepaid debit card account that's online and you have an online account, and they somehow manage to break in, the company might still have some sort of liability or customer support where they'll reimburse you for your losses because they're just, you know, they're going to absorb it in their profit and loss statement just to make sure they can keep the accounts and keep the customers and keep the revenue rolling in. So they don't want you using simple passwords because that increases their exposure as well as increasing your exposure to the loss, because the loss can affect both sides of the equation there. Just like the recent phishing attack I read about yesterday or the day before, some developer at a crypto company fell victim to a phishing attack where they got an email with a Word document that had a macro in it. And they downloaded the macro and they opened the document and Word ran the macro and they compromised some sensitive data that was on their computer, and they managed to steal $55 million in crypto. Right. So whatever they were storing on their machine clearly was not well protected. And I don't know what kind of developer there was for the company, what kind of stuff they have on their machine, but the company itself is not a place you want to do business with, because, you know, a developer's machine shouldn't have anything that can compromise actual production data. All the stuff that they're doing with should be test keys and test data and all that stuff that's not important. And since it's a Word document, they shouldn't be opening up a Word on a server machine, a production server, because macros in Word is a known attack vector. And in fact, the common pattern is you do not have Office installed on a production server. So crypto's a new frontier, right? So there's all kinds of new companies popping up that are, you know, people leasing a 200 square foot office somewhere, and the server farm is just a bunch of old desktops they got on Craigslist or something in the back corner with a power line, maybe a regular business cable modem connecting things into there. So oftentimes in these scenarios, it's what's the quickest thing to market so we can start making money, and the security we'll catch up to that later. So just because, even if it's a big company, right? I mentioned Sony PlayStation Network several years ago, like twice in the same year. All their users' passwords were compromised because they were just stored in a plain text file. Because Word has support for VBA, Visual Basic for applications, so you can write code in Word, and it's going to be able, since you launch Word as you. I don't know if they did a keylogger. The story I read, it basically did. Word has access to the file system, so there's something on the file system that they had. I don't know if it's just a JWT or I'm not very well versed in all the details, but I heard that some of them use JWT it's just a JSON web token to authenticate. Right, it's very common use for JWTs to authenticate you at URU type thing. And it's often just stored as a file on the system. Yeah, so if there's a wallet.dat file, right, it's like a known path or known file name convention that various systems use to store that key data. And then that's all you need. Because I've read stories, people say they've lost their token. They don't have access to their wallet anymore. And companies, there's a couple of companies that will basically go in and like recover. I don't know, right? It's all things I know nothing technical about. Okay, let's see. All right, so we had all this fun stuff for you to read over. So hopefully you had your chance to read it over and take a look at those. So let's go into another. I'm going to skip my numbering a little bit. Let's say 5.4. It's probably good enough for now. All right, so we had modulos are simple one. And we just take the key. And I drop the link to this in the chat. And modulo by value. In the case of hash tables, table size, value. We'll do the division by. Am I frozen? Are we still good? That's saying saved. Okay. Sound check. I'm good. All right. Usually I see people pop on to the drive when I post the link, and I didn't see it happen, so I just wanted to double check. There we go. We've got a ball. Right. So we had the folding. You take the key, break it into pieces, and then mix them together. All right, so MD5 follows this pattern. Then go grab that image. Grab a screenshot. All right, so BC, and D are chunks from the data. Then you have the bitwise operations to fold them together. All right, you can see the keys at the bottom. The thing that looks like an A is for and. The thing that looks like a V is for or. That little sideways L, right? That's just the not. That just means you just flip all the bits. I will leave that bitwise mathematical operations to the computer math class, where you're doing things bitwise. But just really quickly do things 0, 1, and then what an and would be, what an or would be, and we've got X or, and not's just a bit flip, so that's fine. All right, so when you have 2 bits, you have 4 possible combinations. Right, in the case of an and, these are all going to be false until you get to both of them being on. And then it's true in the case of or. Copy this. All we need is any bit to be on and everything is true. In case of XOR, it has to be exactly 1 bit on for the whole thing to be true. Otherwise, false. All right, so if we're doing the not, right, not bit 0, that's just going to flip. All right, 0 becomes 1, and 1 becomes 0. We're not using this symbol over here for the negation. Let's see. One of the ways we can do this radix transformation. Take something from one base and transform that to another base. It's not a very exciting one, but we can get our calculator going here again. Calculator. Jump into programmer. Right, have all our fun bases over here. So in decimal. Oh, got a little bit too big there. All right, hit the enter key or something. All right, all these are the same value. We take those values and you go all the way to base 64. Let's go right. Very happy squirrels. Let's see if it goes the other way around for me. And it doesn't want to go that way. What's that? Where's my encode option? Decode. There we are, encode. All right. Happy squirrels. Right. Same thing, just in base 64. Right. Base 64 is a simple format. 64, give me the wiki for that. There we are. Right, most of it's alpha. And then we got a little bit numeric. All right, so A through Z, and then A through Z again, and 0 through 9, and then there's just 2 other characters, right? Because that gets us up to 62 over 64 from 0 to 62, and then you get a plus and you get a slash. And then one of the characters padding here just to make things are the right size. It's base 64, right? You only need, we got 6 bits. See, my brain's working. 2, 4, 8, 16, 32, right? 64, 6 bits. Base 64 is a common encoding scheme on the internet because all these characters are pretty safe, right? There's just a plus, a dash, and an equal sign for padding. So using this to pass data across the wire, you're safe. Whereas some other characters, things like question marks, my query, string equals something, and another thing equals 1, 2, 3, 4, 5, right? So some characters have special meaning in certain places, right? So in this case, base64 encoding URL doesn't work terribly well because we do have the equal sign in here. We do have the slashes for domain or path separators. But base64 encoded string fits well with a bunch of data formats for not getting in the way of things. And it's something you could do, just go ahead and it's effectively a hash because you're completely changing corresponding output. It's just not a very exciting one. Let's see. Forgotten one. I'll get back to it when I remember. Collision resolution. Copy. All right, so in the context, the hash table, we have two values trying to occupy same space. We have a collision. All right, so linear probing is an open addressing technique for finding an alternative. Ooh, the typing looks pretty bad in it. All right, so quadratic probing. It's also an open addressing technique to find an alternative location to store the value. All right, so linear probing, we offset from the collision point by 1, 2, 3, 4, 5, right? Going on. With quadratic probing, we use the square of the probe attempt. All right, so that gives us 1 square, and let's see if I can get that to go. What is my superscript? I don't remember that one. All right, 1 squared, and then going up from there, 2 squared, 3 squared, etc. Looking for a different place. So let's go ahead and do some linear versus quadratic. And so our data will be, we'll just go ahead and do sequence numbers to start 10 through 70. Table size, let's go ahead and have it be 7. Yeah, it's a little bit too small. Let's make it 11. All right, so our hash values. 10 goes to 10. 20 goes to 9. My brain's working correctly. 30. Let's see. We're going here to 8. 40, question mark, yeah. 40 goes to 7. 50 goes to 6. 60 is going to 5. We seem to be following pattern here. Guess that makes sense. Since I have 2 patterns, that's going to 4. So we're gonna have to go ahead and throw in some extra data here, force a collision or 2. Let's see. Let's add in 51 and 62. So 51 goes to 7 if my brain's working, and 62 also goes to 7. Let's see. I actually have to do this. So we've got our index, we've got our data, pad, index, and data. All right, so this will be with the linear on the left and quadratic on the right. All right, so 10 landed at 10. It divides in 0 times, the remainder of 10. And then our values were just shooting right up. Zero collisioning because of my values and table size had a consistent pattern, but now we're going to go ahead and have some collisioning. All right, 70 already occupies position 4, and then let's see, 51 comes into position 7, so we have a collision here. All right, so linear probe says try 8, try 9, try 10, and then we can drop 51 in. 62 will do the same thing, lands at position 7, occupied, 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 wraps around, and 62 drops in. So with all right, so we had a collision come in, and then we wrapped around, and then dropped 51 in, and then we had another collision, same place, and it wraps around till it finds a spot. So now when 51 comes in, we have the collision again at the same point, and it tries 1 away and finds a collision. So that didn't work out. So we're going to go ahead and do is try 4 away. So 4 away, 1, 2, 3, and then 4. Right, so it skips along before dropping it in where the other probe actually dropped it. And then we go ahead and come along, use different color. Try to drop in 62. Right, we also get the collision. Right, with 62. It also tries 1 away. That's occupied. It also tries 4 away. And then that's also occupied. And now here's where things start to get a little sticky. We're going to try +9. So +4 didn't work. Now we're going to go +9. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So +9 ends up being right 2 before because we're wrapping around, and we get a fun collision. Then we get +16. Let's see, same as -5. 1, 2, 3, 4, 5. If my math's working. Plus 16, we find where 62 wants to go. Whenever we encounter a situation where lots of values end up into the same cell, like we had here with position 7, what we start to get is a little bit of clustering. The idea of quadratic probing, it's a linear probing, linearly, okay, linear probing can suffer from primary clustering, where we have blocks of occupied space inside the table. Ideally, the available space in the table is spread out across the table. This would lead to smaller collision chains and keeps us closer to our big O1 ideal times. Quadratic probing attempts to reduce the amount of clustering by jumping past the primary cluster to keep the primary cluster smaller in size, but it does also have secondary clustering as a byproduct. And so that's just small blocks inside the table, right? Because they're all following the same pattern. All right, so let me show you that. All right, so cluster comparison. Let's grab the table. We'll change the data here though. We'll have, let's see. Let's go ahead and do 5, 16, 6, 17. And what have we got here? 27. We'll add some data after that in a second. All right, so 5 goes to 5. 16 also tries to go to 5, but it collides, so it goes down 1. 6 tries to go to 6, but it collides there, so it goes down 1. 17 wants to go where 6 is, but it collides and it goes down. All right, and then 27, right, that tries to go down to 5, and we'll end up here, right? So these values had, right, 5 went to 5, 16 went to 5, 6 went to 6, 17 went to 6, and then 27 went to 5. All right, so there's 2 locations in the table that we had data trying to go there. Quadratic probe, still the same 2 locations to start, and the same here for 6. Now when 17 comes along, it's going to be right there. And then 27 is going to finally try to jump. My sample data is funny. That is 4 away, isn't it? Right, so 27 comes along, hashes the 5. Doesn't work. Try 16, doesn't work. It's like, okay, maybe we're in a cluster here. So instead of keep iterating down one at a time, we're going to jump. Jumps by 4. 1, 2, 3, 4. So with the data that I pulled out of the air. It happened to be in the same spot, but we actually got there quicker. For the linear probe, it took 1, 2, 3, 4 iterations to get 27 where we needed to be. With the quadratic, it took 1, 2. We happened to find a good spot for it. We have a nice big cluster building here. Let's add some more data. Let's add next. Who's next? 38. 38 also wants to go to 5. Our linear probe, our cluster gets bigger. Here, two-way, the opposite direction. 38 ends up over here. All right, so it keeps a little bit of space. Things will start popping over here more. All right, so when 6 comes along, someone who hashes to 6, it's going to find its way moving in this direction as well. And if we had a really big table, we can see some better clustering and secondary clustering going on with those offsets of 149, 9 away from the insertion point. Double hashing. All right, so clustering problem is a byproduct, right, of following the same pattern. All right, the same offset, the same offsets keep getting used. With the double hash, what we'll do is use a second hash function. For example, say we're using MD5 originally, then we used one of the SHA hash functions. We'll use the SHA hash function, the key, and use that as an offset. All right, in this circumstance, two different keys hashing to the same location in the table would not follow the same jump point or the same direction as each other. Right. From here, we still run into a collision. Can fall back onto the other open addressing iterations. Okay, so let's see. So let's say our hash function 1. Let's just say this is a single character fold. And then hash function 2, double character fold. Killing my words. All right, so let's say our data is apple, peach, pear. What are we gonna do? Kumquat? I can't spell kumquat. Let's do something easier. Let's go for a melon. That seems good enough. Okay, so let's get our table here. Do data, we can do the values, of course, and then the offset from that. Okay. think that's enough columns. Hash 1, hash 2, and then the target location. All right, in fact, let me add any of these. Okay, let's say reap is a new fruit, brand new as of today. So apple, hash 1, just add the values together. Let's see. Let's write a quick program for this because I don't want to do the math manually. And let's use a language that I can write faster in. All right. And value 0 function hash 1 string word range letter and word equals into that letter, and we should be good to go. And let's see what we get here. Then we'll hash choose the same idea, except we're folding 2 of them. All right. So here we go and divide by 2. And that's an odd length word. Let's go ahead and append a character at the end there. Otherwise, we'll loop through. And fold them together. Oh, we're not calculating address. We're just calculating the hash values at the moment. So we'll rip the values out here in a second. I'll show you what's going on. Okay, so let's see. And top equals. We're going to look at value of word sub I. Multiply that by 100 to shift it over. And bottom equals int of word I plus 1. I plus 1. And then values plus equals top plus bottom. So if things are working, whatever, string, oh, my length. Things are working, this will spit out the data we want. So let's go ahead and get my array. Words. I'm going to have 5. Yeah, no, this ain't good. That'll be why that's not lining up. Okay, let's spit out the word plus white space plus our various hashes. And a little bit more white space and hash 2. And let's see if we have anything good going on here or not. Zeros. Okay, bugs in the code. Why aren't you giving my integer value? All right. Time to bust out a real compiler so I can see what I goofed up on. Let's see, where's my data structures? Too much other work going on here. Here you are. I think I have a C# project in here somewhere. Let's grab it. That will I do now. All right. Do. Let's see if I work. Okay. Sounds like a good name. And we get to have some breakpoints while we're here as well. Okay, let's see what's going on with our code. That helps run the right program. Oh, bugs. I don't have bugs. I don't have any data. Helps to have data. Yes, hashing an empty string is 0. Makes sense. So let me go get my data. Where do we have here? Okay, let's give it some data to work with. Garbage in and equals garbage out pattern now, doesn't it? All right. Just run this without debugging so we can validate outputs working better this time. Oh, that's nice and small. All right, so pair and reap being the same 4 letters, both end up at 424 with hash function 1. Hash function 2, since we're pulling things video frozen, is that happening for others as well? All right, well, looks like it's a good time to take a 5-minute Let's run my speed test. Yes, it was a temporary glitch. I'm getting 40. All right, 5-minute break. Okay, so I hear the glitch is gone. Not that I can hear that the glitch was there in the first place, but that's my understanding anyways. Can we confirm? Good now. All right. Let's go back to my output where we are. Here we are. Right. So both pair and reap, being the same 4 letters, produce the same hash value. So when reap comes along, there would be a collision at this point. Right. So let's actually add some more data in here. Let's add some more anagrams. We have APRE and let's just reverse ARPS, double quotes, RPEA, whatever. And didn't want to debug just yet. Let's try that again. Video's paused. Interesting. Yeah, I'm using Visual Studio at the moment. Let me stop sharing and restart the share. Let's see if that helps. It's in the process of stopping, or at least so it seems, if you count a spinny wheel stopping. Guess it wasn't my internet, but rather Zoom this go around for the glitchy. It's entirely possible. Might have to kill Zoom and rejoin. Give it a moment or two to think about it. See what the task manager has to say. And so if I disappear off audio altogether, it's going to be because of that. It's still trying to stop. Okay. Hmm. Looking to see if anything else is going crazy. Well, looks like I'm gonna have to kill Zoom. Shows is not responding anymore. Helps if I unmute myself. Can you hear me now? All right. And the screen's changing. Okay, so back on track. All right, so we have 4 of our keys in here, all hitting the same spot. So the idea here with our second hash, right? So this collision landed at 424. So we want to jump away at 21,313 to look for an available spot. Because my character folding wasn't so great my second go around here, we ended up landing at the same spot. All right, so my secondary position ended up being the same spot again. So we're gonna have that collision. But over here with our other value, right? Two different keys ended up in the same spot. We're trying to do a different offset. So the idea is kind of be like a firework where it just explodes and everyone just starts racing off in their own direction type thing. And so even like two fireworks explode and hit each other midair, right? They're both going to explode and a lot of it is just going to fly off in random directions. And not too much of it will actually hit each other as we're going along there. There can still be some collisions after the fact with our probe sequence, but it's going to be far less detrimental to the overall performance than it was with everyone following the same road as each other. All right, so as far as this code's concerned, wherever I have it here, right? Nothing particularly special. We're just adding the character value of each letter on top of each other, right? So it's our simple single character fold. You just add the values right on top of each other, and then you're good to go. #2, we just increased our fold length to be 2 characters. All right, so we go ahead and let's put a breakpoint here. You can see it happening. Get my windows smaller in size so I can still see. All right, so my word is apple 0 because I did some padding here. All right, so the A and the P are going to be grabbed. A is 97, so we multiply by 100 to go ahead and shift all that data over. And the bottom was 112. And we add that in, I guess. Probably better to shift a little more since we're talking about 3 digits here, but whatever, good enough. And that gives us 9812 for the first 2 letters. And we just keep on adding along. All right, we get another P, and then we get the L, add it all in there, and we're folding the values. My 2-digit shift would work better if I was using capital letters, but either way, folding them onto each other, right? There's all kinds of different ways we can fold these together. But effectively, we're adding AP and PL to each other and then E0 on top of that. And our data is folded. This kind of makes sense at the moment. Right, so we use a completely separate hash function. And what we would be doing with this is use it as an offset. Right, so if we were going to go ahead and right, calculate index. Take the word and size, and then we'll put them together. So yes, well, Dyna is using Unicode, but effectively, yes, ASCII and Unicode is the same for the first 256 values. All right, so value equals #1 for the word, and modulo table size. That's modulo. That's modulo. And then we can go ahead and offset this. Right, so the offset value is #2, the word. And we just go ahead and take our solution point equals our initial hash value normalize, or let's call that index. Hit escape, but enter. Yeah, plus offset, and then we'll normalize that again. By the size, and we can send that back. All right. Add, let's clean this up here. And let's get a tab. There's things out here. Some more tabbing in here, and that'll be good enough. Good enough for what we're doing. Another tab and close out with our calculate index of the word, and whatever 17 is the table size. And hit the wrong button again. Let's do this with the right button. All right, so pair initially tried to go to index 0, so we had a collision. So Reap jumped over to index 11. AppRay also went to the same place because of the way we had our folding. And then RPA jumped in a different direction. So if we start going through all the different combinations of letters that end up in this same spot, we'll start to get more bouncing around. Let's get some more. Let's see. If we go ahead and we can take pair, we can go up, down a letter, and then up letter, AR, and that should give us the same collision. Do the same thing with up a letter and down a letter. Right, because just simple math for a single character folding, same idea, just keep on calling the same thing. C, MNOPQ, P. Every one of these is going to go, you try to go to the same spot. That's enough data. With our double hash, stop clicking the wrong button and get this to work better. All right, even with our small table size, different spot, different spot, different spot, and couple them like 11. Let's see this question here. How do I calculate the values for the offset? So the value for the offset is our collision point. Right, so that's our initial index. That's where everyone's trying to go initially, which is, we can see from pair is 0 because they're all going to this location. And then the second hash. So we hash the same value, our word. We use that as an offset. Whenever we're doing collision resolution, it's an offset from the collision point. Right, so in the case of linear probe, if we hash to index 5, 6, 7, 8, 9 are the indexes that we're going to try next for the quadratic. It's going to be 6, 9, 14, etc. as the indexes that we're going to next there. The double hash, there is not that pre-predictable pattern. It's going to be completely driven off the data and what we've chosen for the second hash function to be for what we're going to be offsetting things by. All right, so let me add some. All right, let's just do the same thing here. We just call, we'll just call calculate index. and have it do all of the printing. Yeah, let's just call it calculate index 2. All right, so we can just do all the printing. That's a funny spelling of void. Let's try that again. All right, so initial hash. Then we have our offset. Let's get our tab in there. Offset location, gives our offset value. And then our, just call it our jump point. Let's see. And okay, calculate index. Cannot rename that. I'm not trying to rename it. I just want to do that. Your version 1. And let's see what we get. All right, so we've got a lot of values, as we intentionally did, trying to go to position 16 in the table. And then we have our secondary offsets, most of which are different. A couple of these are repeated because of the way that we have our folding. And so a lot of these, right? So all these, right? So everyone but that line, 0, 11, 11, 16, 3, 14, 11, 8. Even though they all collided to the same position in the table, they did a fairly good job of spreading out, right? So these multiple hits to 11, so 11 will have to ultimately end up at 12. This 11 ultimately ends up at 13 if we just use a linear probe as our fallback. At least it gives us a good jump point to start to keep, and helps keep our data fairly well spread out. And it's only a 17 element table, and we've already got 2, 4, 6, 8, 10, 11 elements in the table, so it's over half full, almost 2/3, about 2/3 full, and not too bad for our data distribution for where we are in the table. We're going to index 0, 3, 8, 9, maybe 11, 12, and a little bit heavier towards the back end. Key thing of the double hash is it's 2 hash functions. One hash to get us to where we are in the table to start, and then if there's that collision, just run the same key back through a different hash function and use that as an offset to say, okay, that first landing didn't work, so we're going to go try another landing, and then we'll work over in that area. I think so. Grab that screen outputs. Well, that pastes in here. And go. I just got a pop-up saying my internet wasn't the greatest in the world. How are we doing on the audio and video? Surviving. Pause shortly. All right. All right, so I'll just capture the data over here. All right, so the key thing is 2 different functions, one for where we start, one for how much we're going to offset from that starting point. Let's see. double hashing. Oops. Got our linear probing, which is a large explanation in the other doc, quadratic. Another way we can go about this is called chaining. All right, so with chaining, use an array of linked lists. All right, just like the adjacency matrix, where there is a collision, we'll add to the list. All right, so first step, hash the value, the hash function, the list at that position is empty, create the list, and add that value there. If not, insert the value in sorted order into the list. All right, so we'll just have data dash hash value. All right, so whatever the hash function is, don't much care at this point. What we care about is where we're gonna do with our data. So say 10 goes to 5, 20 goes to 7, oops, 30 goes to 4, whatever. 40 comes back to 5, and 25 comes along here to 4. All right. So we'll just have a small table here. 1 second. 2, 4, 6. One more. Give it a nice odd size. And grab my data was. I guess put some numbers here, represent where we are in our lists. Okay, so our first value, 10, comes along. And we want to go ahead and insert that into list 5. Value 10 comes, drop it in. And we have our list state. All right, see if we can get this arrow to behave. Kind of small at the moment. There we go. All right, next state, 20 comes along. Goes into list 7. Probably didn't make my table quite big enough here. I guess we're going to be a nice even number instead. And 20 is over here in this list. All right, so no collisions yet, nothing very exciting. 30 is going to come along, we'll have the same thing. Finds the list. The list was empty, so we go ahead and drop the value in. All right, no collisions with any of these values. Might as well just, yeah, it's good enough. I guess keep one state per data point to start, and then 30's in, and then we're good to go. All right, 40 is going to come along and we'll have our first collision. 40 goes to index 5. That list already has a data point, so we're going to go ahead and insert it in sorted order. So 40 comes after 10. And then we're good to go. Let's see if I can get this down here. All right, now we have 25 going into list 4. That is going to have 30 slide over. And we'll put 25 up front with 35 after it. And the reason why we're putting these values in sorted position is so that our lookup is improved. And so when we do our lookup on data, that didn't work really well. Let's cut this into its own then. If I can grab it. All right, you drawing. All right, so when we do our lookups, when we do lookup for 10, it comes to list 5. Come in here, we find 10. There it is, we're done, we found it. All right, we want to go find 4. And let's say 4 comes to list 7 because of our hash function. First value is 20. Since this data is sorted, I know however long this list is, my data is not in there because 20 is greater than 4, and we can go ahead and stop. And since the most common operation for a hash is going to be lookup, right, the general idea is we'll write a set of records into the table and we'll frequently read from that table. The operation that we want to optimize is our lookups. So if we have to spend a little bit extra time getting the values into the appropriate spot in these lists to improve the lookup performance, then that's what we'll want to do. And that's the general sense for everything that we're talking about in this class. You have a data structure, you have the data you're working on, and you're going to have the various operations for maintaining the data, adding data, updating data, looking up data, removing data. And each of these operations aren't going to be weighted equally for what we need their performance to be. What we want to do is look at what are we spending most of our time doing? Are we spending most of our time writing new values to the structure and rarely deleting, or are we spending a lot of our time just reading data? The operation that we do the most often is the operation that we want to optimize. Right? Because if some operation accounts for 90% of the workload, then that's the operation that will get the most bang for our buck, spending time optimizing it in terms of both software engineering time as well as hardware time. And then there's always the fine balance. How much money do you want to throw at a problem to make the code better versus how much money do you want to spend on adding more nodes to the farm, the corresponding network infrastructure to support that, and all that fun jazz? Because sometimes the solution is you can fix the code or make the code more efficient, and sometimes the solution is that it works good enough as it is, so we'll just go add 2 or 3 more servers and we'll call it good for a few years. And sometimes that's ultimately the end point you have to get to anyways, because if the system keeps on growing, there's a finite limit to how efficient the software can do, right? Even if it's constant time, if the set of data is large, right, and this still takes 3 microseconds to get the operation done, and that's about as good as we're going to be able to get. So if we want to be able to do more, we just need more machines working on the data. All right, so here with chaining, we're just reusing a data structure that we've already been making use of, our array of linked lists. Yes, so the question is, can we have an infinite collision chain here? Yes, you can't have anything infinite, of course. In a computer, because computer is, of course, a finite machine, but there's no arbitrary number to say how long a list can get because it's just a linked list, and linked lists are dynamically growing data structures. You can keep on adding and adding and adding. Now, at some point, for any of these data structures, they're going to get to the point where they're too full, or they've exceeded the ideal load factor. So let's see what time is it. Okay. Talk about what do we do when we have to resize? Resize the data table. It's going to be an involved process. All right, so for all hash tables, regardless of what hash function we're using and what collision resolution we're using. Remember, I forgot to talk about buckets. So back to some later. Buckets, that's the same idea. It's like basically like an adjacency matrix. Swing back to that one later. All right, what collision resolution we're using? So only so much space that we'll have to work with when we start. And there's an acceptable load factor that we want to work with. We want to work with. The next data addition is going to cause us to go beyond what we're happy with. We need right, and we can't just add on to the end the array because the size of the table is part of figuring out where the data is or where the data is going to be added. Thus, we'll have to completely rebuild the table from the previous state. Right, so let's just do our data, modulo. And we'll start with a small table of 3, then we'll do modulo 5, and we'll go to modulo 7. All right, so 10 goes to 1, 0, and 3. 20 goes to 2, whatever, collisions 0, and what we got there, 6. And we're 14. Is that also 2? My brain's working. 4 and 0. All right, so initially we had the table, and let's see. Index data. We'll just do a couple states here. Data. All right, so 0, 1, and 2 for our first case. We had 10 come along. 10 come along to index 1. 20 come along, no collisions, and then we had 14 come along, ignited, and we ended up over here. Right, so we got to a happy state. So we want to go ahead and resize our table. All right, so we can't just do a memory copy and then add a couple rows. Row. And 3 and 4, because on table size of 5, when we try to do a lookup of 10, it says it's supposed to be over at index 0, but before, when our table size was 3, we said it was at index 1, right? So these numbers don't line up in any of my sample data, and probably won't line up with most numbers that we come up with, right? Some of them might end up in the same 0, 1, 2. So these values are all in the wrong spot. So they have to be reinserted. So rebuild the table, drop index 0, get our fun collision with 20. So we move that down to index 1. And then 14 ends up over here at 4. And for some reason we decide, okay, we need to resize again. Same story. Gotta start fresh. 10 goes to 3. 20 goes to 6. Guess I should add my rows. Would help a little bit. Was I never getting 20 goes to 6, right? Okay, 20 goes along to row 6, and then that's 0. And much lower load factors, the probability of a collision diminishes there as well. Let's maybe go back to our files. I should have C# or hash table exercise. Let's see. I forget which one is the one. Is this what I want? No, that's not it. It's more hashing. All right, so we're gonna just go show you .NET doing the resize mechanism. Recall correctly, it starts off table size of 3, keeps things real small. And then builds up from there. All right. Get our size in shape here. I think that's add the table, add the table. Where's my add the table? Here, there we are. Okay. All right, 1525, we'll add some data. So we have here my hash data object, which is just part of .NET library framework called hash table. And it's just a hash table. Deep inside here, we're going to have some buckets. And there's my buckets. We got 3 buckets where we store data. So it's just using the term bucket as a generic term. Bucket's just something you toss something into. So we're going to add our value. Let's see. Okay, let's watch to that. No, watch. All right, so we have our 3 buckets and we drop the value into one of them. It ended up being over here. So we got our key, value, arbitrary data. As we keep adding more data to our table, we're going to get to the point where 3 buckets isn't quite good enough. I think 72% is the threshold for .NET where it says, yeah, it's good enough. Here, so at this point, we want to add another value, and that would you get no collision. We get a perfect hit. We're going to exceed our load factor, so it's going to go ahead and resize our data, and then somewhere in here, our data is going to end up. So now we have 64 position 2, like we had before. It was 15. As I mentioned, right, the table is, regardless of whatever the hash function is actually being used internally by .NET to decide what the value of any given key is, still has to be an indexable value into the table. So that means we got to normalize it to that range and then rebuild the table. So eventually, table sizes will keep on growing as we see the load. And let's get that breakpoint here, because and it's went from 3 to 7. And my table size is a little bit chopped off here, so I guess I need to fix my presentation layer here. Let's move you over there. Let's move both your boxes over. Why do I have table size your choice? I don't remember. Old code. Annoying pop-ups. And it doesn't want to tell me about the extra. That's why it's there. Okay. Anyways, resizing a table means we have to actually rebuild the table. So it can become an expensive operation. So it's always helpful, especially when you're using library code, to know how big things are going to be ahead of time, so you can try to tell it to just make the big bucket to start, so we don't have to go through a dozen or hundreds of resizes as we add to our table. Resizing a table sort of makes sense. Okay. How would you retrieve all the values? We can always just enumerate across the collection. For every non-empty position, you can just spit it out. And again, it's there will be no order to the data. The data more or less appear to be in random order, or at least an arbitrary order, but you can always enumerate it across the underlying array to get all the data, right? So that's what you would be doing when going through the resize. You would create a new table with the new size and just iterate on all the cells. And if it's a non-empty cell, you would just call the insert on the new table. Or if you're just writing a numerator, you just have a numerator, just first cell, and it just iterates until it finds a non-empty cell, and then it can yield back to the color. And then next time they ask for the next item in the enumeration, it does the same thing, it just iterates through until it gets to a non-empty cell. So, which actually leads me to what we're talking about next, which is deleting from a hash table. I'm in the wrong spot. Let's grab the link, drop that along. Get to the right spot. Deleting from a hash table. All right, so deleting first step, find the value. Second step, move the value. Third step, count for the hole that we just created. Yeah, the value could be an object itself. Just depends on, just like we had in the .NET, it was a bucket and the bucket had a key and a value inside. It's probably just a tuple or whatever. And both of which would be pushed into the new structure. Okay, so let's say we have our simple pattern, data, mod 7, and we'll go whatever. 28 goes to 0, 14 goes to 0, 7 goes to 0, 21 goes to 0. Keep things nice and easy, and we'll build our table. That's not what I want. I want a table. And okay, Dex. All right, so 28 was first, so that gets to find its ideal location, and then everyone else just goes through a linear probe, sliding on down from there. So let's go ahead and delete 28. Now let's do our lookups. Lookup for 21. I don't need a whole table. So if we do lookup here for any of these values, lookup 21 comes to 0, not a match, not a match, not a match. We find 21. We say yes, it's in the table. Same thing for 7, 14, 28. If we look for 35 or any other value, all right, we'll see it's not in the table because we find an empty position on the lookup. The question is, the hash table is always an array format? Yes, the hash table is always going to have at least an array component to it. Right, with chaining, it's an array of linked lists. But yeah, the hash table is going to be an array of something. So the element type will be the element type that is sufficient to support what we're trying to do with the hash table. So if it's tailored specific to what we're doing, it might be a little lighter weight, or if it's generic hash table, additional data points might be needed, just like what we're about to talk about here. So let's go ahead and delete 28. All right, so now we're in our new state here. We have a nice big empty cell. So if we do a lookup for 28, 28 comes here, empty cell, that's not 28, no match. What about 14, 7, and 21? 14 hashes to 0. That is not 14. So should we say it's not in the table when it is in the table? Right, clearly not. So what we need to do is we need to account for this empty spot. One way to do this is just go ahead and flag it, set this with a dirty bit, indicating that this cell was previously written to, so it's not in its initial state. So when we do the lookup, right, we're looking for 14. 14 comes to 0. -1 is not 14. So we'll go ahead and keep digging. And we find 14, return it back. And then the same will be true for 7, 21. Right, alternatively, right, so it's marking it dirty. This one here, we're going to go ahead and collapse the chain. All right, so 21, 7, and 14 are all same collision chain. They all go to the same location in the table. So what we can do is we can take the last value from that chain and then go ahead and replace 28 with that value. So then we're going ahead and look up 21. It's immediately where we want it to be. 14, we had to probe. 7, we had to probe. 35, we would come here and find an empty spot and we would stop looking. So dirty bit. When deleting, we either set a bit inside the object or use a sentinel value, right, which indicates a non-empty. So that when we do the lookup, we'll treat the cell as occupied and continue along the collision chain until we find matching key or a cell identified as empty. All right, so with collapse, identify all the values that are a part of the primary collision chain. Grab the last value from that chain, and then move it to the delete point. All right, so let's do a little more complicated scenario here when we have a bunch of other values getting in the way. So we have to be careful that we're pulling the correct pieces from the puzzle here. Right. And let's make this 22. Right, because there's multiple chain unwinding. All right, so we have 28 went to 0. We got 15 at index 1. And let's get some columns here. And all right, so 7, right, went to 0, but it was occupied. Occupied ends up here. And 22 went to 1. It's occupied. Occupied ends up here. All right, so if we go ahead and delete 28 again, right, that creates our hole. So let's do multiple states here. All right, so initially, we'll create an empty spot. 28 also has 7 at the end of its collision chains. We'll take 7. Move that over. We have a hole here. All right, so we have a problem with this hole. This hole needs to see if there was already a collision chain that went past it, because right now we tried to look up for 22. 22 goes to the next one. We find 15, and the next position is a hole. All right, so we're thinking at this point that the data that we're looking for isn't actually there. So we have to keep track and see if there were any other values that were beyond that we need to do additional collapsing on. All right, so it's basically we did delete here, and 22 needs now collapse in to fill that hole. All right, so deleting is probably the most complex operation that we need to be careful with, especially for the open addressing. If it's chaining, it's easy, right? Go to the node, bridge around it, free the memory, good to go. If the list goes from 1 to 0 and it's an empty list, just set to null and we're done, right? Just give the memory back to the heap. So if we have chaining for a collision resolution, it's very, very easy to manage those collision chains because they literally are a chain of nodes. It's a linked list. Whereas the collision chains with our open addressing scheme, that's just a numerical progression that's going 1, 2, 3, 4, 1, 4, 9, 16, where we have to really dig through the values and check what the chains are, because the chains are an abstraction on top of the data set as opposed to actually the data structure itself. How are we doing with the concept of what a collision chain is? All right, let's go ahead and take another 5-minute break and we'll continue on. Okay. Let's see. Any questions about the hash table lab? Seems half of you have it submitted already. Half of you are waiting till the extended due date to go ahead and take a look at it. Somewhere in between. All right, just make sure where it says define a function, you have a function for those parts. Should be a function for each of those parts. Otherwise, you'll lose some credit for not having those functional areas explicitly encapsulated in functions. Let's see. Let's swing back to. All right, test 3 is created. You should already see your updated score. So for that code part, finding the level. Left. Wait. Int level, int data, whatever it is. So before we get to writing the code, let's draw out a tree. Right, this binary search tree. So let's say we have some values like so, whatever, 19. So if we're asking for the value for the node 13, we're not going to be traversing the whole tree because we get to 10, it says go right, we get to 15, it says go left. And the same is going to be true for any node that's in the tree, or if we're looking for 7, which isn't in the tree. Right, we're going to, or 4, say one thing, right, another, right, which actually isn't in the tree. Where I'm most going to be going down one branch. So one of the common mistakes was to write a recursive function that asking the left-hand side, what level is 13? Well, I'm not going to give you an answer for what level 13 is on the left-hand side because 13 doesn't exist on the left-hand side. It's not possible for 13 to exist, right? So we only need to do one branch, and since it's just going to be one branch, we can do this iteratively. Right, so we can start the level off at 0. We can do our test here if there's no tree. Or just do a temp. Let's just do node star temp equals root. And while temp is not equal to 0. That's fine. Look at while loops. Do while there. Okay. All right. So if temp data, whatever I call it, is equal to data, go ahead and just return back the level because we found we're looking for, right? So say we're looking for 10. Temp comes along. Sorry. So we call our function level, pass 10 along, we set temp equals root. Temp's not null. Temp data is the root. The value of the root is 10. 10 is equal to 10. And we return 0 and indicate back that the root is on level 0. If that's not the case, we're going to have to go ahead and go down the tree. So another mistake that was commonly made, people were not putting their increment in the right place. So it was either not going up or it wasn't going up correctly. and make a decision if the data is less than the node that we're looking at right now. Then we can go ahead and have temp work its way down to the left. Temp equals temp left. Otherwise, same story, but different direction. Right, so we had, I guess I shouldn't have killed my tree. Whatever, draw it back. Draw it back. All right, so we had 10, 15, 13. And that covers our scenarios for the most part. Let's say we're looking for 15, pass 15 in, temp's root. 10 and 15 are not equal, so we don't break out of our loop, increment our level. And then data is not less, right? We're looking for 13, so that's greater. So temp goes to temp right. So temp's over here at 15. That's not null. Temp data is 15. We're looking for 13, so that's not true. Increment our level. It is less than, so we go ahead and come down here to 13. Temp's at 13. Temp data is 13. Data is 13. Level is presently at 2. Return back 2, and we're done. And so now we just need to account for our negative case. Let's say we're looking for 5. And 5 isn't actually, where did my eraser go? There you are. 5 is not actually in the table. All right, so temp's not null. 5 and 10 are not equal. 5 is less than, temp equals temp left. Temp is now null, and we break out of the loop. So then there's just a matter of indicating that data is not in the tree, so we just say -1. So we find it, return back the level that we built up to, or we run off a branch of the tree, we break out of our loop, and we return -1. And of course, there's lots of different ways that you can slice this up, as long as it gives the right level, whether you're doing 0-based or 1-based. All you do is change that. Now it's a 1-based leveling, 10's on level 1 instead of level 0. Just a matter of what the value of this hard-coded constant is going to be. If you want to go a different numbering system for the levels. Does this make sense? And so remember, for your trees, just because recursion is a common pattern doesn't mean it's the always pattern. I think, am I doing a traversal or am I doing a branch? Right, just like adding is going to dig its way through a branch, so it doesn't need to be recursive. All right. Any questions about any of the other questions for test 3? Yeah. So the question is, the one while loop temp data is equal to data, it breaks that loop because return keyword, right? That's a jump statement, just like break, go to and continue. Where return causes us to leave the function that we're in. So that means leave the loop or any number of loops and then leave the function, setting the return value to the value of our variable level here. And there's no more processing needed to be done. I think the average of the test was 81% before I even did the grading of the remaining 8%. So I'm guessing 86, 87% or something like that was the test average. So numbers are good for that test. So practice test for next week. Test. Good old graphs. Graphs, just because of the nature of graphs, going to be a harder test than trees. Trees is just a subset of graphs. Now we're dealing with the whole big old graph party. So which of these questions do we need to go over the answers for, or you've already taken this 2, 3, 5 times over and you've figured everything out based off of the answers? Or shall we go through the practice test?
It would be cool to go through the practice test.
Let's practice the practice test. All right. Okay, so depth first search starting at vertex A. And here's the corresponding table to help us track things. Right, so we're starting at A. And A is the first output. So one first output. Depth first search says I have a choice between B and D. And the table says B is who we're going to go to first. So B will be the second output. From here, I have two options, C and E. B says, I don't want to go to A, I've already been there, so we'll go to C. So C is my third option. C gives me one option for something we haven't been to already. So that gives us our fourth. Two options again here from F. Won't go back to C because we've already been there. So we'll go ahead and go to E. So now I have our fifth output, D and H from E. Been there. So we go to D. Sixth output, and then not much of a way of options at this point. So our fourth output should be F, and the last would be I. So I don't know why these aren't in order. Let's see if I can try to remember to try to fix that. And I. Questions on number 1. Right, so remember, the adjacency matrix or list is maintained in alphabetical order. So when it's differentiating between the options, it's going to be going in the same order that is the underlying data structure. Since that's data structure is alphabetical, that's why we went to B first instead of D first. Right? It's not arbitrary, it's based off of the underlying data structure. And I see I at both, well, that's just a 1. So that's me typing a 1. It might have been in 2 places in this list here. That's always possible. Yeah. Yep, green is my lettering. All right. Good to move to number 2. So I was doing a breadth first search. All right, also starting at A. Here we're going to go ahead and NQ B and D. Our unknown neighbors, right? So we know about B, we know about A, we know about D. So I'm going to mark those off. And we'll go ahead and DQ. So here's our question. Yeah, so it doesn't matter where B and D are in the drawing of the graph. We would always go to B first before D because B is in matrix before D. And for either of these, for either the depth first or the breadth first, when we're differentiating between our options, the decision is based off the underlying data structure. And we came along to record A and it said, go ahead and NQ B and D because we don't know about them yet. All right, so we DQ B. Come to B's list. We already know about A, so we don't need to NQ it. We don't know about C. So we'll NQ that. We don't know about E, so we'll NQ that. Then we can go ahead and DQ. So D pulls off. Is our third output. We go to D's list. Okay, so we know about C, we know about E. So we know about A, we don't care about that. We know about E, we don't care about that. But G is new information. So we'll go ahead and NQ G. Then we go and DQ C. Let's print that out. C, already know about B. No new information. We don't know about F. So we go ahead and NQ that. DQ again. E gets us to our fifth. Coming to E, we already know about B. We already know about D. We forgot to mark it off. We know about F. We don't know about H. So we're going into U. G's up next. G's our sixth output. G, we already know about D, and we already know about H. So there's no information, no new information from G. So go ahead and TQF is our seventh. No information about C or E, but I is new information. So we can NQ that. I forgot to slash that out. So all information is now known. So just be HI after that for 8 and 9. So our second vertex would be B. B, wherever you're hiding. Fourth vertex is C. And the last happens to also be I again because of the shape of the graph. Questions about number 2? And with this particular breath verse, we can see we're pretty much creating some levels here for how we're going through this depth away, right? So these first two, right? These are both 1 hops away. Then we had our 2 hops. Then we had our 3 hops. 1, 2, 3, 4. Yeah, 4 hops. As our depths. Questions? Everyone's got their screen grabs, side notes. Good to clear the screen. All right. Okay. Where the fourth output was C, because we had 1, 2, 3, because we do all those that are both. So we do the ones that are 0 away, we do the ones that are 1 away, then we do the ones that are 2 away. 2 away, 2 away, 2 away. So we had 1, 2, 3, 4 outputs. C is the fourth output. Because we'll output all the nodes that are 1 hop away before we output any of the nodes that are 2 hop away, and we'll output all the nodes that are 2 hops away before we get to those that are 3. Right, because we got 1 hop, 1 hop. We got 2 hops, 2 hops, and 2 hops. And then we had 3 hops and 3 hops, and then lastly 4 hops. Right. C and G at all be the same depth away from the root, but because C is alphabetically before and because B is alphabetically before, we start processing B before we start processing D, and B tells us about C and E. Yeah, so if we were just to swap the letters B and D here, then E would be the fourth output because B would tell us about E and G. So E would be in the queue earlier on. And then we would get to B, the D over here, and it would tell us about C, and C would be later on. So it'd be A, B, D, E, G, C if we were to swap the letters of B and D here in this graph. Okay. Does this graph have a Hamiltonian circuit? All right, so right here in the middle with this big old cut vertex, which would cause our graph to become disconnected into two graphs here. So it's not going to have a circuit. Right? Because if we try to go ahead and go along, right, I can get to this point, but that means if we're repeating it and I can't get to this part. So no circuit, but we could. Right, so we stop one short of that cut vertex, create a trail. All right, so it does not have a circuit, so that is false. Euler's easier to find out, right? We just go ahead and just look at the numbers. That's 2, that's 2, that's 2, 4, 2 and 2. Everyone's even. So we have our Eulerian circuit. Prim's minimum spanning tree. Right, so starting at vertex A is in the tree. And we have 3 options for which to grow the tree. Prim being one of our greedy algorithms, chooses the closest vertex not in the tree to be added to the tree. We throw away this 9 edge because that 3 is better to get to F, and we now add 2 to the equation. Choosing between 2, and this one's already consumed, so we'll go ahead and circle it. 2, 3, and 5, so we'll take the road to H. This new data about 5 is irrelevant because we have a better edge at 3. So we'll go ahead and move along to 3. And this edge tells us about that 3 and that 8. Choice between 5, 3, and 8. Take 3. And I'm already going further than I need to because I already got my first 3 added nodes are F, G, and H. F, G, and H. Well, if we were to keep going, D would be next. So we'll just keep on going while we're here. And D, that tells us about this 4, which supplants this 5 as a way to get to B. Tells us about this 1. Tells us about that 6, which supplants that 8 for getting to E. Right, well, the 1 edge. And we can eliminate this 4 because we found a, oops, found a better way. Get to B. All right, 2 edges to consider. Take the 2. No new information from this point. Take the 6, and we have our minimum spanning tree. Questions for number 5. Number 5 is alive. It'd be kind of funny, make a graph and it's looking like a robot once it's done. Probably a little bit too much work. Anyways. Seems we have no questions for Prim here. All right, if we were to all of a sudden change this to be Kruskal, right, we would be sorting, adding our 1 edges. And I did that, or AG would add first because AG is alphabetical, CD. Then we choose, we have right, BC as a 2, no cycles, GH is a 2, no cycle, 3s, AF, no cycle, DF, no cycle. And we go ahead and create a cycle with 4 there, kill it. Create a cycle with that 5, and then we would kill it. Create a cycle with that 5, so we would kill that. And then we get to our 6 and we're done. All right, so if I were to ask Kruskal 1 was ask this to say which edges are broken in the process, right? So these are the ones that I X'd out. So BD, AB, and FH were the edges that got broken because they created cycles from the tree. All right, so the tree starts off as empty, just a bunch of vertices with no edges. We add edges to the tree and that edge creates a cycle, then we break that edge back out. Why is FE not crossed? Because we stopped. There's no reason to go any further. Any edge that we would add at this point is going to be heavier than any edge that's already in the tree because Kruskal sorts the edges, which means they're guaranteed to just be removed. So it's an unnecessary effort, so we stop. Once we have V-1 edges successfully added to the tree, the algorithm completes. Or is completed. All right. Moving along, number 6. We didn't start anywhere. We started with the smallest edge. There were 2 edges tied for smallest at 1. AG would be in the list first because of the way we find edges, right? We go A's list, and we add the first edge to our list, right? We just basically just do an insertion sort. Grab the next edge, insert it into our list. Grab the next edge, insert into our list. So the earlier lists in alphabetical order will end up in the list first and be added first. Right, so if we had this matrix, we'd have A goes to B, and A goes to F, and A goes to G. So those are 3 edges. So AB gets added in the list first, then AF comes along and then goes in front of AB because it's 3, and then AG comes along and that's the beginning of the list. So we have 1, 3, and 5 in my sorted list so far, and then we go to B next, and we just keep on adding. Right. So remember when we're sorting the list, we're not sorting from a drawing, we're sorting from the underlying data structure. And that there is exactly one underlying, there's exactly one state the underlying data structure can have for this graph. That's ABC, D, E, F, G, H as the labeling for the array of linked lists, or as the labeling for the matrix on both horizontal and vertical axes. Right, when we're working with our computer systems, we like to be deterministic wherever possible. Is it the same graph or different graph? Okay, I guess I just did it. All right, okay, so let's actually do it again. All right, A, G, C, D, and B, C, G, H, A, F, D, F. And then we start getting to our cycles. First cycle is BD. Then we had a B. And we had FH. All right. And let's see if I misclicked anybody. Doesn't seem I did. All right. And there's that one. Any other questions for our test that will be in class next week on Monday? Presuming there aren't any storms, earthquake, fires, or any other natural disasters that were to impede such an operation. So the coding questions that you might find on the graph test would be just like the data structures, which array of linked lists. So or our two-dimensional array for the matrix. The other code we get to would be for Floyd-Warshall's all-pair shortest path, which is just nested loops, working on underlying graph matrix. But that one we didn't actually write code, we got pseudocode, so it'd be on the pseudocode realm if we see that on the test. Otherwise, there really isn't any much code, too much code on the graphs test, because there's not really anything that new that's in graph code. You're just using arrays of things, and you're just working in there, right? So the graph matrix labs and lists pretty much covers what we need for the code, because all the algorithms just gear themselves on top of those data structures. So you determine which list you need to go into, or which row you need to go to, and then which column you need to go into to determine if it's a neighbor or not, what the cost is to get to that neighbor, and things like that. So the algorithms are understanding the algorithms and be able to work through the algorithms, not so much code the algorithms. But if you understand any algorithm, in theory, you can code the algorithm as long as you understand the code for the underlying data structure that's modeling the information. Yeah, so the code for this test to be like lab exercise code that we had, if you see any code. All right, that leaves us about 25 minutes for lab. We have that hash lab to work on. So there isn't any additional lecture that we need to go over tonight. Like I was saying earlier, the test is again in class on Monday towards the beginning of class. Is the most common pattern we have so far. It's been a little bit an inconsistent pattern this particular semester due to holidays and things like that. But yeah, again, it's in class, 65 minutes. Be there if you have questions to ask in Canvas while we're taking the test, and then we will carry on the other materials after we're done with the test. All right, I'll keep the Zoom open. If you're, let's see, where are we in the programs? Make sure I'm not forgetting anything else we should be talking about at this point. Program 5 is doing 4 weeks. Program 4 rather. We'll talk about program 4 next time. It's hashing. It's a little bit more involved programmatically on this one. Okay, so we're good. Got lab questions or other questions, wherever you fire them at me, but there is nothing else to lecture on for tonight. Balance for times break in lab.
Hey, Professor. I actually had a question about NumPy. I don't know if you have any experience with that.
NumPy. Is that one word or two?
One word. Yeah, that one right there. Basically, I was looking at doing array operations, stuff for, I guess, like multiplying two arrays together or two matrices together. You'd have to do like
Okay, sure.
nested loops. But I heard somewhere that NumPy actually does it way faster because it uses vectorization. I don't really understand how you would do something like vectorization in C++ or something like that. Do you have any idea how to?
Well, standard template library has vectors. The vector is it's just a dynamically sized array basically. So you can just keep pushing on either end if you want, and then it'll grow itself on its own.
But I mean, like to do like a dot product or something like that to arrays.
Yeah, it just probably has code that's, you know, specialized just for the purpose of doing that. Yeah, array computing. So yeah, it's just got specialized code for that purpose. I don't know that. I don't think I've actually ever personally written. Matrix math is not a very common math being done. You'll see it a lot with image processing and things like that, because or you might, if you want to transpose an image or rotate an image 90 degrees, something like that, that's all matrix math for that kind of stuff.
Yeah, I actually that happened to me in a project, and I was unable to really get it to run in any kind of reasonable time. And in fact, it like crashed with larger images and stuff. So
Yeah,
sort
yeah,
of my.
yeah, I'm sure there's all kinds of bitwise operations, right? Because you're more or less swapping pixels, right? And there's mathematically a way to swap two values by doing ors and ands type things. So you don't actually do like a copy to like the typical way you do a swap, temp equals value one equals value two, and then value two equals temp, right? But there's a way to actually do it in like two statements with some bitwise operations. So it's probably got that type of optimization in there. So it's keep feeding in mathematical instructions ALU instead of just doing much memory movements around.
Oh, I got it.
Uh,
Okay. Yeah, I'll look into that then. Thank you.
yeah. So Chloe, no, chaining and open addressing are two different ways of collision resolution. Open addressing is the way where we just bounce around different indexes, versus chaining just a linked list. A library and API are not the same thing. API, which is application programming interface, is what you would code to. So like, for example, NumPy here, it is a library and it will have an API where it exposes certain touch points that you would consume. But inside the library, there could be internal private functionality that you wouldn't expose to the outside. So they're definitely related to each other, but the API is what you expose to the world, right? So you might have some like public web APIs, for example, that you could just call into, right? So various services, it's kind of like RSS back in the day. The RSS was just a standard XML format that you could pull data from various places. But here you can get more like weather IO. Let's see, what do they have? Do you do Swagger in here or what? Yeah, they kind of have things here. So the API is basically function calls. So they're exposing a function called, get date. What's the current date on your server type thing? Because you're connected to one of the Nest servers, so you have a very accurate date time information, and it just expects its parameters. And then on the inside of their library code, there's gonna be just the core logic and all that fun stuff. Sure, what websites are good for visualizing. Let me see if I have any links. What links do I have already? No, I don't think I have anything. Right, so what you can do, Sarah, is you can go ahead and just create some graphs. And then you can just post them in Discord and post your solutions, and we can work over that the output generated is correct for that given graph. I imagine there probably are some visualizers out there, but I don't have those handy or recall if I ever had any of those. Yep, it's images, very easy to just screen grab it. Windows Shift S is screen grab. You make your image in Paint or whatever. Just drop it in Slack and carry it on from there. Just drop it in the test channel.